All right, so we left off in the last video introducing the idea of a gravitational field or a gravitational force field. And the motivation for this is going to come from a fact from physics that that talks about the relationship between two masses, two objects with mass, and the force due to gravity between them. So this little formula is something that we get straight out of physics. The lowercase m and the uppercase m represent the masses of two objects. Typically, the larger or the more massive object is the capital M. G is a constant; it's the gravitational constant, and R is the distance between the two objects. And so we have this relationship from physics: the force or the magnitude of the force due to gravity between two objects is the product of the masses with the gravitational constant divided by the square of the distance between them. So what we want to do is take this, which is just the magnitude of the force, and get a better description of that force in terms of a vector field. So to motivate that, let's try and take the two objects that we're looking at, little m and big M, and put them in 3 space. And to simplify things, we're going to position the object that has a mass of capital M at the origin, and then we're going to say that the object that has a mass of lowercase m is at the point xyz, so that its position vector would look like this, position vector with components x, y, z. Okay. Now, if you can picture that in 3 space, the magnitude of that vector, or sorry, not the magnitude, the distance from between these two masses is the distance from the origin to the point x, y, z. So that's what our function here, or our formula here, is calling r. But given that we're labeling this vector as this bold x represents this vector, we could alternatively write r as the magnitude of x. It would represent the distance from the initial point of this vector to the terminal point, that is the large mass to the smaller mass. The formula uses r squared, so r squared could also be written as the magnitude of x squared. Okay, so now if the larger object was placed at the origin, then the smaller object is going to be pulled toward the larger object due to that gravitational force. And so because the gravitational force is acting toward the origin, that's opposite the direction of x. If this is a position vector, then its initial point will be at the origin and its terminal point will be at xyz, so it's pointing away from the origin. If we wanted to determine a unit vector that's pointing in the direction of the gravitational force acting on this object, then we want the negative of this vector divided by its magnitude. We're dividing by its magnitude because that's what makes it a unit vector, and the negative changes the direction, so it points toward the origin. Okay, so now how then do we determine the gravitational force as a vector field? Well, what we would want to do is take the magnitude of the force and multiply that to the unit vector to turn that into a vector with the correct magnitude. So that's what's happening here. Here's my unit vector. There's the negative x over magnitude of x, and we're multiplying by the force due to gravity that we get from physics. But this can be simplified because this force, the magnitude of this force, is given by this formula here. And if I change the r squared into the magnitude of x squared, and then multiply that to this magnitude of x that's showing up here, I'm going to get the magnitude of x cubed down here. mmg is showing up here as well. And then this x, remember, is the vector x. So this bold x right here is a vector. Everything else is a scalar that's being multiplied to that vector. Okay. Now, written this way, again, this is a vector field because the input x is a vector, the output is another vector. In fact, it's a vector, it's a scalar multiple of this vector here. And as I'm looking at this, I think the negative appears to be missing, so I'm going to make sure and write that in there. There's a negative that should be there. Okay, so if we were to take this x and expand it, or not expand it, but write it in component form x, y, z. So if I were to write this as the component form x, y, z, and then distribute this scalar into there, and then if I were also to use the fact that the magnitude of x is equal to the square root of x squared plus y squared plus z squared, those are the components of x, then cubing that takes that 1/2 power and makes it a 3/2 power. All of that amounts to this, an alternative and a definitely messier version of this vector field that we have here. But this makes it a little bit more clear what the components of each vector in our vector field look like. I'm writing it in this form because we're going to use it in this form a little bit later. Okay, so again, this particular vector field we would call a gravitational field. And if you were to plot this gravitational field, what you would see is all of the vectors pointing toward the origin, which we've kind of argued why that would be the case. I think your book shows a diagram of that. I just didn't include that here. Okay, so that's gravitational fields. And then, like I said before, any vector field that's meant to represent forces acting on points in space, or points in the plane, if you have an interpretation that works that way. We can think of those as particles as well. Then we refer to that vector field as a force field. Again, it sounds very science fiction, but that's a term that we use specifically when the vector fields represent forces. Okay. Next up, we're going to return to the topic of gradients. So back in chapter 14, we defined the gradient this way. The gradient of a multivariable function f of xy is equal to the partial with respect to x, I, plus the partial with respect to y, j. If this was a 3-variable function, then I would also have a partial with respect to z, k out here. But either way you look at it, the gradient is actually a vector field, because if you notice, the input is a vector, 2 components in this case, or 3 components if we're talking about f of x, y, z. And the output is also a vector. I have an I component and a j component in this case. So we haven't been using that terminology up until this point, but now we can start calling it what it is, which is a vector field. In particular, we call vector fields that are gradients of some function gradient fields, or sometimes your book also refers to them as gradient vector fields sometimes. These are a really important type of vector field that we're going to study in greater depth throughout this chapter. But there's some terminology associated with these also, which we'll get to. Let's look at an example, though. This is another example out of your book. I wanted to use it because it gives a good diagram that would be difficult to draw by hand. But let's read this. So it says, find the gradient field of the function f of xy equals x squared y minus y cubed, and then plot the gradient field together with the level curves of f. Your book calls it a contour map, which is just another name for the graph of the level curves of some multivariable function. So let's start with the gradient. I need the gradient of f x y equals, okay, so I need the partial with respect to x. That's going to be treated like a constant. It's going to go away. I'm going to get 2xy I for my I component, and then differentiate with respect to y. I'll get x squared here, so plus x squared minus 3y squared, and that's going to be my j component. Okay. Now, again, this was done by software, and your book just has this image in it. But if the reason we're doing this second part here, where we want to plot both the vector field, which is all the blue arrows, that's this vector field right here, with the level curves of the original function, f of xy, is to verify something that we knew was true from back in chapter 14. We talked about how the gradient of a function, a 2-variable function at any point, is always going to be orthogonal to the level curve at that point. And we see that happening here. You see these level curves up here, how they kind of curve outwards, and you can see the vectors, these arrows, appear to have that orthogonal relationship with each of these level curves. So this is kind of establishing that connection once again, something we've already discussed. Okay. 16.1 is the shortest section in chapter 16. Right away, section 16.2 gets much longer, but this is the last little bit that we have to talk about in 16.1. So still on the topic of gradient fields, if you have a vector field f, and I'm using a capital F here, such that f is the gradient of some other function, little f. So this is the relationship right here. Big F is equal to the gradient of little f. Then this vector field right here, big F, we refer to as a conservative vector field. The lowercase f that we took the gradient of to get big F is called a potential function for f. It's very similar to an antiderivative. It's technically not that, but because the gradient can be thought of as kind of a derivative, then you can kind of think of little f as an antiderivative of big F. But you notice we're not using that terminology. We call it a potential function, and we'll make the reason for that that terminology clear in a different section. But I do want to point out that it's going to be of great interest to us later to be able to determine when a function is a conservative vector field or not. Notice if it really were that we were just looking for an antiderivative or something, that would be kind of a quick way of verifying if we could find an anti-gradient, if that were a thing, of this function to determine that yes, this is in fact a conservative vector field. But it's not quite as simple as that. And not every function is a conservative vector field. Not every vector field is a conservative vector field. However, the ones that are, many of the ones that are, have very natural and useful interpretations in physics. So down here we're going to show that the gravitational force field that we talked about previously is a conservative vector field. And as we're going to see once we get into some work with line integrals, you can do some useful things with conservative vector fields that you can't do with other types. So let's wrap this up by showing that the gravitational force field we talked about before is in fact a conservative vector field. Right now, because we don't have any theorems for determining whether something is a conservative vector field, the only way we can do this is from the definition. We need to find some potential function for capital F and verify that that potential function, once we take its gradient, gets us to f. So down here, this is the form that I had put the gravitational field that we came up with on the previous page in. It's in component form. And really, it just comes down to verifying that this thing is the gradient of this function right here. Now, this, again, is right out of your book, but if you want, you can verify that if I took the gradient of this function, and it's a three-variable function, x, y, z, so you're going to have three components in your vector here, you would, in fact, get this. So that is enough to verify that this is a conservative vector field because that this is a conservative vector field because we found a potential function whose gradient is equal to this. Okay, that's going to be it for 16.1.